Welcome to our lesson on logarithmic functions and their properties. In this video, we'll cover everything you need to know about logarithms, starting with their definition and then exploring their key properties, also known as the laws of logarithms. By the end of this video, you'll have a solid understanding of logarithms and how to work with them. Let's start with the definition of a logarithm. For any positive real number, a, whereas not equal to 1, and any positive real number x, y equals log base of x if and only if a raised to the power of y equals x. In simpler terms, the logarithm base of x is the exponent to which we must raise a to get x. For example, log base 2 of 8 equals 3, because 2 raised to the power of 3 equals 8. Before diving into the properties, let's understand the domain and range of logarithmic functions. The domain of a logarithmic function is all positive real numbers, as we can't take the logarithm of 0 or negative numbers. The range is all real numbers, meaning a logarithm can output any real number. Additionally, the base must be positive and not equal to 1. Let's visualize the graph of logarithmic functions to better understand their behavior. Here we have the graph of y equals log base 10 of x, also written as y equals log of x. Notice that the graph passes through the point 1, 0. Because log of 1 is always 0 regardless of the base. It also passes through the point 10, 1, because log base 10 of 10 equals 1. The graph has a vertical asymptote at x equals 0, meaning the function is undefined at x equals 0 and approaches negative infinity as x approaches 0. For logarithms with base greater than 1, like our example, the function increases as x increases, but at a decreasing rate. For bases between 0 and 1, the graph would be decreasing. Now, let's explore the fundamental properties or laws of logarithms that make them powerful tools in mathematics. There are three main properties we'll cover: the product rule, the quotient rule, and the power rule. Let's start with the product rule. The logarithm of a product equals the sum of the logarithms of the factors. In mathematical form, log base a of u times v equals log base of u plus log base of v. We can prove this using the definition of logarithms. If we set log base of u equals p and log base of v equals q, then by definition, a raised to p equals u and a raised to q equals v. So u times v equals a raised to p times a raised to q, which equals a raised to the power of p plus q. Taking the logarithm of both sides, we get log base of u times v equals p plus q, which is log base of u plus log base of v. Let's look at an example. Log base 2 of 8 times 4. This equals log base 2 of 32, which is 5. Using the product rule, we can also calculate this as log base 2 of 8 plus log base 2 of 4, which is 3 plus 2, giving us 5. Next, let's look at the quotient rule. The logarithm of a quotient equals the logarithm of the numerator minus the logarithm of the denominator. Mathematically, log base of u divided by v equals log base I of u minus log base of v. The proof is similar to the product rule. If u equals a raised to p and v equals a raised to q, then u divided by v equals a raised to p divided by a raised to q, which equals a raised to the power of p minus q. Taking the logarithm of both sides, we get log base of u divided by v equals p minus q, which is log base of u minus log base of v. For example, log base 10 of 100 divided by 5 equals log base 10 of 20, which is approximately 1.301. Using the quotient rule, we can calculate this as log base 10 of 100 minus log base 10 of 5, which is 2 minus approximately 0.699, giving us the same result of approximately 1.301. Now, let's explore the power rule. The logarithm of a number raised to a power equals the power times the logarithm of the number. In mathematical notation, log base of u raised to the power of k equals k times log base of u. To prove this, if u equals a raised to p, then u raised to k equals a raised to p times k. Taking the logarithm of both sides, we get log base of u raised to k equals p times k, which is k times log base of u. For example, log base 3 of 9 squared equals log base 3 of 81, which is 4. Using the power rule, we can calculate this as 2 times log base 3 of 9, which is 2 times 2, giving us 4. One more important property to know is the change of base formula. This formula allows us to convert logarithms from one base to another, which is particularly useful when using calculators that typically only have natural logarithm, ln, or base 10 logarithm functions. The formula states that log base a of x equals log base b of x divided by log base b of a, where b is any positive number not equal to 1. The most common cases use either the natural logarithm, base e, or the common logarithm, base 10 log base a, of x equals the natural log of x divided by the natural log of a, or log base of x equals log base 10 of x divided by log base 10 of a. For example, to calculate log base 2 of 7, we can use the formula. Log base 2 of 7 equals the natural log of 7 divided by the natural log of 2, which is approximately 1.946 divided by 0.693, giving us approximately 2.807. There are a couple of special logarithm values worth remembering. First, the logarithm of 1 with any base is always 0. This is because any number raised to the power of 0 equals 1. Second, the logarithm of the base itself is always 1. For example, log base 10 of 10 equals 1, because 10 raised to the power of 1 is 10. Let's look at a practical example that combines multiple logarithm properties. Suppose we want to simplify the expression log base 5 of the quantity 25 times the cube root of 125. First, we can use the product rule to separate the logarithm of the product. Log base 5 of 25 times the cube root of 125 equals log base 5 of 25 plus log base 5 of the cube root of 125. For the first term, we can use the power rule, since 25 equals 5 squared. Log base 5 of 25 equals log base 5 of 5 squared, which equals 2 times log base 5 of 5, which is 2 times 1, or simply 2. For the second term, we can use both the power rule and the fact that 125 equals 5 cubed. Log base 5 of the cube root of 125 equals log base 5 of 125 raised to the power of 1/3, which equals 1/3 times log base 5 of 125, which equals 1/3 times log base 5 of 5 cubed, which equals 1/3 times 3, which is 1. Finally, combining both terms, we get 2 plus 1, which equals 3. So, log base 5 of the quantity 25 times the cube root of 125 equals 3. To summarize what we've learned about logarithmic functions and their properties, first, we define a logarithm as the exponent to which we raise the base to get a certain number. We explored the 3 fundamental properties of logarithms: the product rule, where the logarithm of a product equals the sum of the logarithms; the quotient rule, where the logarithm of a quotient equals the difference of the logarithms; the power rule, where the logarithm of a power equals the power times the logarithm. We also learned about the change of base formula, which allows us to convert between different logarithm bases. And finally, we saw how to apply these properties to simplify logarithmic expressions. Logarithms have numerous applications in science, engineering, computer science, and finance. They're used to model phenomena like earthquake intensity, sound volume, pH levels, and compound interest. Understanding logarithms and their properties is essential for solving exponential equations and working with exponential growth and decay problems. Thank you for watching. Practice using these properties, and you'll become proficient in working with logarithmic functions.